So the title of my presentation is Plasmonic Metasurfaces, and I'm going to describe their functioning principles and also put quite some emphasis on the nanofabrication of these metasurfaces. The Institute of Technology is located in the French part of Switzerland, French-speaking part of Switzerland, and not very far from Geneva. I must say today, unfortunately, it's not as sunny as on the pictures, but whenever you come to Europe, please let me know. I'll be delighted to welcome you to EPFL. If you are interested in some of the publications, you can find them on our website here. And if you would like to have a copy of the slides, I will be, of course, very happy to share them with you. Just send me an email. I thought that maybe not all of you are fully familiar with plasmonics. So I would like to start with a very brief introduction about what plasmonic is. A way to understand plasmonics is to look at the light scattered by a small particle. If we have a small particle, say, of metal, like silver, we would describe this small particle with its permittivity. And the permittivity, of course, depends on the wavelengths. This is a dispersive material. If you shine some light on this particle, the amount of light that is scattered will follow this formula. And in that formula, we have two terms. You see the first term here depends on the radius of the particle. The larger the particle, the more it is going to scatter light. But it's actually the radius divided by the wavelengths. So if the wavelength is very small, there will be a lot of scattered light. And this term is actually responsible for having blue sky. If you look at the sky, not straight into the sun, but really looking at the diffuse light, it appears blue because this is the shortest wavelengths, the shorter wavelengths that we find here, that our eye can perceive. In plasmonics, we don't use this term, we actually use the second term. And you see this term here, again in the denominator, we have the permittivity. The permittivity of the material is, for metal, a complex function, so it has a real part. You see here for silver as a function of the wavelengths, the real part, and in blue, the imaginary part. And this term here has epsilon plus 2, so it means that if we have a material that has a permittivity which is minus 2, we will have minus 2 plus 2, so we will have 0, and dividing by 0 make things very, very large. So this condition for silver of having epsilon equal to minus 2 will occur at a specific wavelength. And at this specific wavelength, about 350 nanometer, we have a strong scattering, very, very strong scattering peak, which will give the particle its color. We call that plasmon resonance because in the metal that will work for plasmonics, we have a lot of free electrons, and this behaves like a plasma, not a gas plasma like in a luminescent tube, but a solid state plasma where you have a lot of free electrons. So from this very simple theory, we can deduct that if we look at small silver nanoparticles, they should appear blue because they will scatter a lot of light at the wavelengths where epsilon is equal to minus 2. And if you do the experiment looking at dark field microscope, then you observe that indeed the particles are blue. But very surprisingly, you also see that some appear green, some yellow, or some even red. And these are all colloidal nanoparticles that are all the same size, about 50 nanometer. So to try to understand what was going on when I was at UCSD, we took the same image in an electron microscope. And then we try to magnify as much as possible these nanostructures. And you see that this one, which appears nicely blue, is a nice sphere. But this one here, which is green, turns out to be like a pentagon. And this one, which is red, turns out to be a triangular nanoparticle. So we have different sizes, different shapes, and therefore different colors. And I know that all of you are very versed in optics, so you're going to tell me, well, this is just a geometrical optical resonance effect. This is true, but what is very fascinating is that this resonance occurs for particles that are much, much smaller than the wavelengths. If you want to make a strong resonance, you normally need an object that has a size comparable to the wavelengths. If you are in your bathtub and you want to make a big wave, you're not going to flip gently your hands around. You're going to move forward and backward into your bath until you make a wave which has a wavelength comparable to the size of your bathtub. And that's not the case here. So it's something special is definitely happening in these nanostructures. And also, another consequence is that if we look at plasmonic metals, we look at large, we rarely see such a huge bar of silver, but if you would look at a large bar of silver, it would appear just gray, reflecting most of the light. But if you look at nanostructures made out of silver, you have a lot of very different vivid colors. So this works with silver and it works with a few other metals. But unfortunately, there are not many metals that are plasmonic metals. These metals actually have a very nice name. They're called Carnage Metal. Coinage comes from coin because these are actually metals that have a strong interaction with light and that are often used for making coins. So we have gold, silver, aluminum, copper, tungsten. And the criterion for having this strong optical resonance is that these materials have a very, very high density of free electrons. Of course, the condition that we have seen, epsilon equal to -2, will be different for each metal. So aluminum, silver, copper will have different resonance wavelengths and will produce plasmonic effects in different parts of the visible spectrum. Usually when one presents plasmonics at this stage, it is customary to say that actually, by the way, our ancestors were putting some very small particles of gold into the glass paste they used to make stained glass windows. And because the gold will stay in the glass forever, then it will support these strong optical resonances. And this is why still today we can enjoy these very strong resonances in stained glass window, even after centuries. So I'll come back to that at the end of the talk. But for the time being, after this very brief introduction to plasmonics, let me move into technology. I think it's a field where technology is really very important. So let me move to the nanofabrication of plasmonic nanostructures. And there are basically two ways of fabricating nanostructures. One which is quite popular, which is shown here, and it relies on having a positive resist. So you have a substrate. We are going to write in the photoresist using an electron beam. And you see the resist is called a positive resist because once we have written with the electron and we develop the photoresist, we have here apertures in the system. So in these apertures, we then deposit the metal. Actually, we deposit the metal everywhere, but the metal will come in contact with the substrate just in these openings. And then we do what we call lift off. It means we just put the entire sample in acetone and the photoresist is going to be dissolved and the nanostructures will just remain where they were written. I am showing here the utilization of 2 layers of photoresist. This is important because if I magnify here, we have, you see an overhang in that region. So we have an overhang, and this overhang is necessary such that when we deposit the metal, we have a non-continuous film between the top layer and the bottom layer here. If we don't do that, then we risk having the metal being continuous, and when we try to dissolve the photoresist to do the lift-off, we risk tearing apart the metal and having structures that are very poorly defined. So this is the standard technique. We open the photoresist, if you like, and we evaporate the metal at the end of the process. The other technique is based on using a so-called negative photoresist. And for that technique, we start by depositing metal like gold. We deposit gold on the substrate. we put the photoresist on top, we write the same structures, but now because the photoresist is negative, instead of exposing the structure where the e-beam has written, it will leave the photoresist, which is going to become very hard and stay where we want to define our structures. And then we bombard the entire substrate with ions. So we use this ion beam milling, and it's going to remove the metal everywhere. And the photoresist will protect the structure that we want to keep. So it's interesting to compare the two approaches, and this is what I do on this slide. You see, if we use the etching approach to define, these are all gold nanostructures. For example, a dipole antenna made from 2 gold nanoparticles, or ring, or what we call a dolmen structure, which will support some phanoresonance. We see that the structures that have been fabricated by etching actually are much better defined. We can have here a gap which is just a few nanometers, whereas if we use liftoff, it's not the case. The structure are actually not so well defined. Actually, if you try to do something like a spiral, you can do that with etching, but if you try to do it with liftoff, you see it doesn't work. If you try to have something like a donut with an opening in the middle, it works with etching, but it doesn't work with liftoff. And the etching approach, I think, is superior, but it's not being used a lot yet. So I hope in the future it's something that will be picked up to fabricate very, very tiny structures. I've mentioned that we have only a few plasmonic metals, aluminum, silver, copper, gold. And the question we raised was actually, could we extend this range of metal? And the route that we have followed, I had a very good Indian young lady as a PhD student who just graduated, and she had this idea of looking into using alloys. So alloys, that would be a mixture of gold and silver. And the idea is that if we can mix gold and silver in alloys, we will be able to have material with a dielectric function that will lie between the dielectric function of silver in gray and the dielectric function of gold. And you see that indeed, and these are measurements, the dashed line are from a model by Ryu, but the solid line are measurements, and you see that indeed it seems you can fabricate plasmonic alloys that will have different stoichiometry and will have different dielectric functions. But of course, alloying is something not very new, especially gold and silver, they alloy very well, but normally the alloying is performed at a very high temperature. But for our research, we would like to have nanostructures made out of alloy. So the shape of the structure is very, very important for the optical effect we want to study. Unfortunately, if you perform alloying at high temperature, normally you will not be able to maintain the shape of the nanostructure. You see it here. If you try to fabricate some small rods made out of alloy, and you heat your sample to perform the alloying, then your particles are lost and they just become some circles. So the question we addressed was, would it be possible actually to find a low temperature alloying procedure that would enable any alloy composition just with the standard equipment we have, and then that would maintain the size of the nanostructures? And what Deb Data found was actually, yes, we can do that by alloying at a low temperature, quite a low temperature, only 300 degrees Celsius, but for a very long time. And actually, after trial and error, she discovered that it's also good in the end to have a little booster of half an hour at a higher temperature, so 450 degrees. What's interesting in this approach is that you start by depositing 2 metals. For example, you deposit 80 nanometer of gold, and then you deposit 20 nanometer of silver on top. Then you do this low temperature alloying, and you have an alloy which has a stoichiometry of 80% gold, 20% silver. You can do another deposition where you put 20 nanometer of gold, 80 nanometer of silver, you alloy it, and then you have an alloy which would have a composition of 20% gold, 80% silver. And what's really nice is that if you try to make shapes like triangles, we've seen at the very beginning that triangle had this very strong optical response. This is the structure before annealing, and this is the structure after the low temperature annealing. And you see that the shape is really very well maintained. You can do long structures. You can have a high aspect ratio, and the shape is also well maintained. Or you can do what we call photoresonant structures. So it's a collection of 4 nanostructures, again, made out of the alloy with that stoichiometry. And you see that after alloying, it is very well preserved. We can look at the structure. Obviously, something is happening. We see that the roughness changes. Our main concern was, is this really an alloy? Have we really mixed the two materials? If we do EDX analysis, we see that indeed we have everywhere on our sample a mixture of gold and silver. We had also a little bit of titanium for adhesion, but probably more interestingly, if we do XPS, we see that as we go through the substrate, through the sample all the way to the substrate, we have really a mixture of gold and silver, in that case, 20% gold, 80% silver, and this is through the entire wafer. Keep in mind, if I go back, when we started, we had something that was inhomogeneous. We had silver on top, gold at the bottom, but now we have really a homogeneous alloy with the same stoichiometry all the way through. So we were quite proud of that technology, but the question was, well, actually, can we do something with that? And can this be of any use? And to try to address this question, I would like to come back to these resonances. Resonances, they are often shown like that. You have a strong peak in the amplitude. So for example, I have a small metal nanostructure, I shine light, and when I have the right resonance wavelengths, then at this resonance wavelengths, I have a strong peak in the intensity of the scattered light. This is also what I explained at the beginning when I was briefly describing the plasmon resonances. But actually there is more when you have a resonance. There is more to just having a strong amplitude. And if I may, I'd like to try to do a small experiment. So I will stop sharing my screen, go back just to the camera, and I will show you a very sophisticated experiment, which is a mass here and a spring. Okay, it's not nothing very complicated, but I'm sure you do that for your students. So if I move my hand very slowly, you see that the mass goes up when my hand goes up and goes down when my hand goes down. I'm at a very low frequency. If now I go at high frequency, there comes a point where I've gone through the resonance of the spring, where actually what happens is that my hand goes down, but the mass goes up. And when my hand goes up, the mass goes down. So let me go back to my presentation. At low frequency, when the hand goes down, the mass goes down. When the hand goes up, the mass goes up. But if I go at high frequency, then it's the opposite. When the hand goes down, the mass goes up, and vice versa. So what this means is that in addition to having a strong amplitude at the resonance, there is also a phase change. Here it is in phase, here it is out of phase. This is the case for a mass and spring system, but it's also the case for the light scattered from the particle. If we work at low frequency, as is the case here, we see that the scattered light is in phase with the incoming light. But if we work at a high frequency, if we go beyond the resonance of the particle, in that case, the plasmon resonance of the particle, we see that the scattered light is out of phase compared to the incident light. So we can control the phase of the system. And why is that important? Because I think it's fair to say that most optical systems, they work with the phase. For example, if you look at a grating, for a grating, you will have a plane wave coming at normal incidence, and the light is going to be scattered going at an angle. So it means that the phase front arriving here will have no phase difference, but you see here there will be a small phase added to this phase front, and here there will be more phase added, and here even more, until we reach the next phase front, and here we have a phase of 2 pi between these successive phase front. A lens works with the same principle. A lens will focus light because it's going to add phase or subtract phase to the incoming plane wave. And of course, the most general case is that of a hologram. A hologram also works by engineering the phase on the hologram to produce the hologram image. So the idea is, can we now mimic the response of an optical component using different plasmonic nanostructures on the surface? And this is what has given rise to this term of metasurface. So on the surface, we have a collection of different nanostructures, and each nanostructure is going to produce a specific phase. The special thing here is that we would like to do that not with different shapes, but just with different stoichiometry for the composition. So we'll have different alloys on the surface, and we can hopefully mimic this type of response. So from a technology point of view, it's quite demanding, because what you have to do is first start with your substrate, then do some E-beam, then evaporate metals. Say you would evaporate 20 nanometer of gold, 80 nanometer of silver. Then we restart and we redo another E-beam to write other structures. And for those structures, we could then deposit 80 nanometer of gold and 20 nanometer of silver. And then we remove all that and we alloy the structure. So then we would have on the same substrate different nanostructures with different stoichiometry. And our dream is to see whether they would behave like, say, a hologram or some optical element. So this is the sample that has been fabricated. So you see here different nanostructures. If you look at them, you would say, well, maybe they are not so well aligned. You see these two are not perfectly aligned with these two, but you must keep in mind that they have been done in successive E-beam writing. Because what we have here now on our sample are a collection of different nanostructures with different stoichiometry. Some have 20% gold, 80% silver, and others have the opposite, 80% gold, 20% silver. And if we now shine light on this metasurface, this is what we get. So this one is working as a hologram. We can also make it work as a lens. So in that case, we have actually a very nice focus, which is really diffraction limited, produced by this lens. And this is the surface that produces that. So it's a combination of different alloys with different stoichiometry that will produce different phases and then produce this optical effect. Let me move on another topic, which I'm also quite interested in, and that's the question about trying to make a pure magnetic effect using a plasmonic system. This goes also in the more general trend of these metamaterials and metasurfaces, so collection of nanostructures that will build some unusual optical effect. And one interesting question is whether we can, with this system, produce a pure magnetic response. If you go back to the fundamentals, like the book of Landau and Lifshitz, you will see that actually it is clearly written you cannot produce magnetism at optical frequencies, because to produce magnetism, you need currents, and current cannot be sustained at very high optical frequencies. But it turns out that you can actually. So magnetism does exist at optical frequencies, but of course you cannot produce magnetism by having a permeability, so a mu, What you need to do is you have to tailor the epsilon, the electric permittivity. And plasmonic materials are certainly good candidate for this because they have a strong response. But unfortunately, this magnetic enhancement is always accompanied with an enhancement of the electric response as well. So what does that mean? Let's look at this little silver U-shaped particle, and we look at its response as a function of the wavelengths. We see that we have different peaks in the scattering cross-section. Now, these peaks in black for the scattering cross-section, we can decompose them in multipoles, like the electric dipole, the electric quadrupole, or the magnetic dipole. So our dream would be to find a system where actually there would only be a magnetic dipole, and these two terms would be negligible. But we see that if we look again here, that actually the response is always dominated by the electric response in blue, the electric dipole, and the magnetic effect are usually very, very small. So the question is, can we engineer our system such that we would have something that would be essentially magnetic? To do that, we have taken two silver nanoparticles and we put them close together. The bar here is 100 nanometers, so they are 80 nanometers long on the surface. And we illuminate this system. If we illuminate the two particles at normal incidence, the two particles are going to be driven in phase. You see the field is going to go forth and back in those two in a synchronous way. But if we come at an angle, we can have a delay between that particle and that particle. And as a consequence, you see the delay, and the blue and the red, they show the polarization charges. So because it's a metal, it has a lot of free electrons, and these free electrons, they move, they can all go on one side where it would become blue. Because they have all gone on one side, the other side of the particle will have a deficit in electrons, and it will be appearing positively charged, so say in red. So this mode looks like a bit of a small current loop. So it looks like a magnetic mode. This mode, on the other hand, is typical of an electric dipole resonance. How is it if we make the analysis of that system? If we look first at normal incidence, so this is when we excite this mode, we can decompose the scattered light into these different modes, and we see that the dominant mode is this electric dipole. If we come at 45 degrees, now we start to see what we are after. We would like to favor this magnetic dipole mode, which is here. So we would like to have this mode very strong. But we see that in that case, it's still the electric dipole in blue, which is the strongest one. And also we have a little bit of electric quadrupole here. We see it here in this graph. The electric dipole is very strong. We start to have a little bit of magnetic dipole. The dipole, they are just vectors and they can have different orientation. And here we also have a little bit of electric quadrupole. A quadrupole is a tensor, so you have these 9 elements. But still, it's this electric effect that's dominating. We would like to have only this one to dominate. So what can we do? Well, the reason for that is that the delay between these two rods is not large enough. So to increase the delay when we come at an angle, what we can do is to make an asymmetric system. Like we can have a small bar, it's going to be 70 nanometer, and a long bar, which is going to be 90 nanometer. And we put them close together, so they couple. And we see that the response becomes quite different, depending whether we come at normal incidence, at 45 degrees, or from the other side at minus 45 degrees. We also observe a very good agreement between this calculation and the experimentally measured response. Now, the question is, when we analyze the system, it turns out, if we look, we focus here at this wavelength of 680 nanometer, we have been now capable of removing completely this electric dipole resonance. So we have a strong magnetic dipole that we see here, but we still have an electric quadrupole here. And we see it here again in the distribution. So we start to have a strong magnetic response, but there is still this electric quadrupolar resonance. I would also like maybe to make a brief statement here. I think there has been a bit of confusion sometimes when one has started to talk about having these magnetic effects at optical frequencies between this electric quadrupole, which is certainly an electrical mode, but it has some similarities with a current loop, but it's not a magnetic mode, and the magnetic dipole, which is really truly a magnetic mode. So what's happening here actually, the fact that we have these two resonances is because in that system with the two bars, when we come at oblique incidence, so the one is illuminated first and then this one, so there is a delay between them, we have actually the two modes that are degenerate. We have a superposition of the magnetic dipole. The magnetic dipole is really like a small loop of current, and the electric quadrupole, which is more like a half a loop of current, if you want. So the final step in this experiment was to try to remove this degeneracy, and it was possible by splitting each bar into two. So now we have a structure with 4 bars, and you see that depending on the polarization, for example, if you come with transverse electric polarization, you will drive this in that direction, and then because of the retardation, it will be driven in the other direction, and thus will really make a small loop of current, so a magnetic dipole. On the other hand, if you have transverse magnetic polarization, then you drive these two guys differently, forth and back, and this is the electric quadrupole. So we did, again, this experiment, we did the calculation, we did the measurement of the response, and you see here in this analysis that indeed here we have been able to have almost 100% magnetic light. So it's mainly only this magnetic dipole that is strong. The other terms have disappeared, the electric quadrupole and the electric quadrupole here and the electric dipole here. So the system is going to radiate like a magnetic dipole. It means it's going to radiate relatively isotropically. So you have this dipole that's oriented in the Z direction, and the intensity of the light is going to be constant. This is actually what we measure in the optical microscope. This is the radiation pattern. We have to block the incoming light, so this is why here there is this little circle, this little black disk, but we see beyond that we have indeed light that is radiated isotropically in very good agreement with what we calculate from the simulation. And if you look at different polarization, X or Y polarization, you see these patterns that turn around. So you really have something that is radiating like that, like a circular beam, if you like. If you change the polarization, if you go with the transverse magnetic, then you excite, in that case, mainly the electric quadrupolar mode, and the other modes are, at least the magnetic dipole is pretty much inexistent, and there is a little bit of electric dipole as well. So it's possible to have a system in which you produce light that is scattered just like magnetic light. And this is done with a metallic system, so a plasmonic system, which normally has a response which is dominated by the electric effect, not the magnetic effects. Now there is another actually class of nanostructures where magnetic effects are very prominent. And this is dielectric nanostructures. So a metallic nanostructure will mainly support dipolar, electric dipolar mode, but a dielectric resonator can support many other modes including magnetic dipolar modes. So a question we were having was actually, can we combine both worlds and access some interesting effects? So we've done that. We have fabricated these structures that combine, for the dielectric part, a silicon cylinder. We have here a relatively large silicon cylinder, which is about 400 nanometer in diameter. And as plasmonic structure, we use aluminum, so we have an aluminum disc. And we also wanted to control the interaction between the two, so this is why we had here this dielectric spacer made out of glass. You see here the structures as a top view or here as a side view. So we were able to fabricate a lot of them on the same substrate. The process actually is also quite interesting. So if you are versed in technology, let me just briefly explain how we fabricate these structures. We start with a substrate of glass because we do all our experiments in glass. So in that case, fused silica, so that we can look at the optical properties through the substrate. We put a thin coating of alumina, and what's more interesting, and this is really where the structure starts to be built, is that we put silicon. That's going to be the main body, the dielectric resonator, and then on top we put glass here in green. On top of that, we're going to do lithography to build the aluminum disc. So again, we put photoresist on top. We illuminate with electron beam and we develop, so we end up having an aperture, and in that aperture we deposit aluminum, and we use this aluminum actually for two purposes. The aluminum is going to become the plasmonic part of our structure, but it's also the mask that we will use to define the structure. So what we are doing here in that step is, again, using etching, like ion beam etching. In that case, we can even use reactive ion etching to remove the material around the shadow of this aluminum disc, such that at the end, we have here this structure that is built from a silicon cylinder, a small spacer of glass, and then aluminum disc on the top. You see that since the aluminum disc has been used as a mask for the etching, it gets a little tiny bit damaged. You see here the rounded edges of the aluminum disc, but nonetheless, this still keeps its good plasmonic properties. Here you see the glass, and here you see the silicon. When we look at the response of that system, we have on the one side this plasmonic aluminum disc, which basically has an electric dipole resonance. And here we have this cylinder, silicon cylinder, which will support many, many different modes. Again, it will have a very strong magnetic dipole as well. We see it here in black. At this wavelength, we have a strong magnetic dipole. It's the dominant lowest energy mode for these dielectric structures. And then when we put them together, we end up having quite a complicated response. So we have many, many different peaks. These are just calculations. When we do look at the measurement, this is what we get. So this is here, you see these different peaks. And because we have different features, like we have peaks here, we have a little dip here, here we have another dip and another peak here, we thought all these different elements, we could use them for doing biosensing. One major application of plasmonics is to do biosensing, so to look at the attachment, for example, of molecules on the surface of the metal, and when the molecules are adsorbed on the surface of the plasmonic nanostructure, it changes the plasmon resonance, and this change can be quite significant. We've not looked at a very sophisticated sensing. What we did was to compare the response of our nanostructures for different background, which were in red just air, in light blue water, and then we added a little bit of sugar in the water to have another refractive index, so 1.4, 1.44. And you see that as we increase the refractive index of the background, we have a shift of these different modes. And each mode actually shifts a bit differently. We can summarize that by introducing what is called the sensitivity, which in sensing is expressed as nanometer per refractive index unit. So that means that if we look, for example, at this feature, when we change the background by 1 unit of refractive index, this feature is going to shift by a certain wavelength range. So we have a wavelength range per change of refractive index. So this is why this sensitivity is expressed here as nanometer per refractive index unit. These are the values, and each feature has a different sensitivity. The one that's the most sensitive, number 2 here, so the orange feature here, has actually a sensitivity of 200 nanometer per refractive index unit. So if I were to change the background where my structures are immersed by 1 full refractive index, the resonance would shift by 208 nanometer. Actually, when we saw that, we were quite disappointed because if you take standard conventional state-of-the-art plasmonic system, the sensitivity is much better. It's in the order of 600 nanometer per refractive index unit. So we have a very complicated structure, and actually it's not so sensitive. Even if you compare with dielectric structures like waveguide or dielectric resonator integrated on a waveguide, there also their sensitivity is better. It's in the order of 300 nanometer. We thought, well, maybe we can try to improve on that. And we were guided by simulations. You see here our structure with the silicon cylinder, the glass spacer, and the aluminum disc. When we computed the field intensity distribution, it turns out that most of the strong field, so the field which is going to change the response of the system, is inside this dielectric spacer. So we thought, could we actually make this field access the outside world so that it would notice when the outside world, so the liquid surrounding the system, changes its refractive index. And we see that if we etch a little bit this glass disc, then we can access, in that case, the outside world. The field becomes strong here in the background. It was possible to do that by having an additional wet etch step, and then we would etch away just the glass. It would not etch the aluminum or the silicon. And this is what it produces. Actually, it looks like very nice cupcakes, but these are true nanostructures that have just been colored. You see the silicon substrate, the silicon cylinder, then the glass spacer, which is in green, and on top you have the aluminum. The aluminum is very grainy. This is something you have to live with. Aluminum is grainy, but it doesn't really matter because the field is going to oscillate here horizontally, and these grains are basically vertical, so they're not going to disturb the response of the system too much. Providing access to the analyte to the strong field actually increased the sensitivity, but the improvement is quite modest. It's only 40 nanometer by refractive index unit. So altogether, we have now a sensitivity which is in the order of 245 nanometer per refractive index unit. It's a very nice, very interesting structure. Probably one could do better and more with that structure. It was just a very first trial. Okay, let me just finish and come back to this question about what our ancestors did. Did they really put gold nanostructures into the glass paste? We are lucky to have a center on stained glass windows not far from my university. And this is an amazing place where they have a lot of cardboard boxes with pieces of stained glass windows from all ages and from all around the world. And we were able to put our hand on a little tiny bit of glass that comes from the Minster of Ulm, which was built in the late Middle Ages and which is famous for having very nice stained glass windows. So we thought, okay, probably this must have some gold because it has a nice reddish color. And we put a little tiny bit of that sample onto a substrate, and we could observe that indeed there is a region where there is a nice, strong color effect. Now, when we did EDX of this sample and we were hoping to find gold or maybe silver, we were disappointed because we didn't find any gold or any silver in that system. But actually, we were lucky to find and very pleased to see that we find another plasmonic metal, which is copper. Copper is not so much used nowadays as a plasmonic metal, but it is a plasmonic metal. It has quite high losses, so this is probably why it's not used. But you see, it has a very strong optical effect. And this is produced just by tiny copper nanostructures. Their size is in the order of 60 nanometer, and they are extremely diluted because the distance between neighboring particles is several microns. So this again illustrates how strong these optical effects can be when you use plasmonic nanostructures, even just using copper, which is not the strongest plasmonic metal. From the scattering cross-section of a small copper nanoparticle, you can actually compute the color, and there is a very good agreement with the reddish color that we observe with our experiment on this little piece of glass. So that brings me to my summary. I've shown you that nanofabrication is a very important enabler for these plasmonics, and different approaches can be used, but this approach based on etching, which is not so much widespread yet, works extremely well and allows you fabricating very small structures that are very, very well controlled. We have developed a low temperature alloying process which can be used to fabricate nanostructures that can then be turned into metasurfaces. And here, this is an example of a hologram based on that principle. We've seen that it is possible to make pure magnetic response of a plasmonic system, which is surprising because normally it would have an electric response, but it is possible if you trick it a little bit to get a pure magnetic response. And finally, some interesting combination of plasmonic metal like aluminum and dielectric to produce hybrid metasurfaces. Of course, all this is only possible because I'm very privileged to have amazing collaborators, and I'm of course also very grateful for our different sponsors. Again, you'll find all the publications here on the website. Thank you very much